Hi everyone, and welcome to today's Physics Daily Booster. This is the first one in our Paper 2 series. We've obviously got to start this before you sit Paper 1 because otherwise they just won't fit in between the two physics papers. This is on the advanced information for both the foundation physics and the higher tier physics. What we're going to do then is start off with the first bit of P5. So P5 is all about waves. When we talk about waves, we're talking about an oscillation that transfers energy from one place to another. And realistically, what we've got are two types of wave that we can divide things up into. We have mechanical waves that need a medium to travel. Things like sound and water are mechanical waves. Or we have electromagnetic waves which do not need a medium to travel. So really what we're doing here is splitting them into their two types based on if they need something to travel through or not. Electromagnetic waves don't, sound and water, the mechanical waves, do. As far as our waves go, we will classify them as either transverse or longitudinal. If we think transverse waves first of all, then this is where the vibrations are at right angles to the direction the wave travels. And what we can see is this little diagram in the bottom left gives us the diagram for a transverse wave. So notice the oscillations on the left hand side there of the graph are at 90 degrees to the direction that the wave is moving. In our longitudinal waves, the vibrations are in the same direction that the wave travels. So diagram on the right there shows us this one, and you can see we've got these little regions where it's closer together. So in our longitudinal wave on that diagram, you can see there's little areas where the lines are very close together called compressions, so they're high pressure regions. And then in between those we've got these more spaced out lines, which are the rarefactions, low pressure regions. If we go back to the one on the left in our transverse waves, notice how we basically have peaks and troughs. So the high point is the peak, the low point is the trough. We've got four key terms to know about properties of waves. So you need to know what it is and how we actually measure it or mark it on a diagram. First one, amplitude. This is the distance from the middle line to the top or the bottom of the wave. So you can choose, but from that midline, you're either going right to the very top of the wave, the peak, or right down to the bottom, the trough. Now, this is usually measured in meters. Wavelength is next, distance from one point on a wave to the identical point on the next. Easiest usually to mark this as peak to peak or trough to trough, but it could be any point on one wave to exactly the same point on the next. This is measured in meters. Your frequency is the number of waves or oscillations per second, and that's measured in hertz. And your time period is the time it takes for one wave to pass a given point. And because it's time, we measure in seconds. When it comes to actually representing our waves in graphical form, then we've got a choice. We can use time trace or a snapshot. Both of those graphs will allow us to work out the amplitude, midline to the top of the peak or the bottom of the trough. Doesn't matter which one we've got, same thing for amplitude. The other measurement that we take is going to depend on which type of graph we have. And the way we know which type we've got is the label on the x-axis. So we can see the one on the left has got time on the x-axis, therefore that is our time trace. So the time trace just shows how displacement varies with time at any given point. Now, from the time trace, what we can do is measure the time period. One point on a wave to the identical point on the next. However many seconds that takes, that is our time period. If they were to give you just a numerical value of the frequency and ask you to calculate the time period, all you need to do is 1 divided by frequency to get that. Option number 2 of how we can represent this wave is on a snapshot. We'll know it's a snapshot because the x-axis is distance. So this is just showing us how displacement varies with distance at any given time. And what we're going to then be able to do is measure the wavelength. So quite simply, one point on a wave to the identical point on the next, that is then the wavelength because we're measuring the distance at the bottom there in meters. In terms of how we can observe waves, because most waves are just travelling through the air now, you can't see them. So how can we observe waves and take measurements? The most likely way to do this is using a ripple tank. Now, our ripple tank is what we can see in the little picture on the left here. It's a little plastic tray with water, and then we've got some kind of little bar that's going to create waves, basically creates the ripples. Now, what we can do is measure either wavelength or frequency using our ripple tank. And there's two ways to do each. So if we look at measuring wavelength first of all, in order to measure the wavelength, you can literally just drop a ruler into the ripple tank, and then start it off. As those little waves are travelling, you're then going to try to judge, obviously, the distance between them. Not easy, because obviously they are moving. Therefore, an improvement is we're going to use this bit of equipment called a stroboscope, which basically acts like a strobe light. So what we will then get is a frozen wave, and then we can measure it using a ruler, because it just stops the waves, or at least it appears to stop the wave, so that you can then get a more accurate measurement. Second option for what we can measure in our ripple tank is the frequency. So what we do here is just place a little marker, so something like a little dot on the edge of the tank, and we count how many waves pass that point each second. So that's not literally you would count for a single second, you'd normally count for about 30 seconds and then obviously divide by 30. Alternatively, we could place a little piece of paper that just touches the top of the bar, and therefore as it vibrates, basically you're going to hear a little sound as it taps on the paper, and you can count those instead. This one is listed on both of the advanced informations as one of the PAGs, the speed of sound PAG. This was on a paper a few years ago now about how we could carry out an experiment in order to work out the speed of sound. So they gave you kind of two people and asked you to design an experiment that would give you accurate results, I think it was. Now, the key thing here is that we need measurements of distance and time, because remember, speed is distance divided by time. So what we're going to do with our little people is we're going to get them to stand a set distance apart and measure that distance using a ruler. We're then going to do something to generate a sound. In this case, it might be shouting, hitting something, anything at all that makes a sound. And then we're going to time how long it takes for the other person to hear it. Once we've got those two measurements, what we can do is distance divided by time gives us our speed. How do we make sure that these results are as accurate as possible? We're going to repeat it several times, and then we're going to take a mean. We're going to identify any anomalous results in there and obviously discount those before we calculate the mean, but that should give you plenty of marks on that style of question. There is another option. We can use technology and use a couple of microphones that are a known distance apart, which are connected onto an oscilloscope. You make a sound, and then using the oscilloscope you can work out how long it takes for that sound to reach the two different microphones. Again, distance divided by time gives us our speed. That leads us very nicely onto our calculation, the first one of paper 2, which is wave velocity is frequency times wavelength. Again, this is on the formula sheet, you don't need to memorise it, but do remember to look out for the wavelength being in meters. If it's in centimetres, divide by 100 to convert to meters first of all. And do remember that when we're talking about the velocity of our sound, it is going to vary dependent on temperature and pressure through which that sound is going to travel. Obviously, if there are bits we've gone through today that you'd like to look at in a bit more detail, you do have the P5 playlist on the main channel, your revision guides, your class notes, and I do strongly recommend looking at some of the old exam papers so you can see things like the speed of sound experiment question from the past. And then of course don't forget to join us again tomorrow for our next Daily Booster.